And so now let's move on to mantras from Vedic period during 1000 BCE. So it invoked powers of 10 from 100 all the way up to trillion. So during that time, meron na silang pag nagagamit na nila yung mga powers of tens. So powers of 10 like before na ginagamit din natin ngayon. So bago pa natin magamit 'yan, nagagamit na pala 'yan ng mga Indians during the Vedic period, 'di ba? So ganun kagaling yung mga Indians sa paggamit ng math. Next is they provide evidence of use of arithmetic operations such as addition, subtractions, multiplication, fractions, squares, cubes, and roots. So gumagamit na rin sila ng mga addition, subtraction, multiplication, at iba pang mga arithmetic operation during that time. So, bago pa natin malaman yun, nagagamit na ng mga Indian yun during the Vedic period. Okay, so that's the contribution of Indians during the Vedic period. So let's move on to the Sanskrit text. So Sanskrit is a very familiar word for every one of us kasi madalas natin ito ma-encounter. So the Sanskrit text during 4th century CE. So yun daw Sanskrit ay there are reports that Buddha enumerating numbers up to 10 to the 53 as well as describing 6 more numbering system and above this, leading to number equivalent to 10 to the 421. So, during that time, nagagamit na talaga yung powers of 10 na yung Sanskrit text nga ay, kung mababasa natin yung Sanskrit text or makikita natin, meron doong, naglalaman siya na may report doon na si Buddha ay gumamit na ng ganong klase ng mathematics or arithmetic operation. So, ganun yung nilalaman ng Sanskrit text. And for you guys, para maintindihan yung Sanskrit text, so this is the example of Sanskrit text that I've researched on Google. Ayan. So, this is the Sanskrit text. So, hindi natin mababasa yan. Pero I know for a fact na there are representation of numbers. As you can see, there are geometrical shapes here. The triangles, squares, and rectangles na nakikita nyo. So, yan. Parang may mga nakikita akong numbers like this, 20, 40, yan. Yan. So, yan yung nilalaman ng Sanskrit text. Meron na silang evidence na yung math is nag-i-exist na during that time. So, next, the Sulba Sutra. The Sulba Sutra is one of the ancient texts contain procedures about the building of ceremonial platforms. So, konting kalaman lang, yung sutra is a fire. Para siyang fire of altars sa mga altar. Apoy sa altar. So, that's the meaning of sutra. So, yung Sulba Sutra is naglalaman siya ng mga procedures sa pagtatayo ng mga ceremonial platform. So, ayun, as nasabi ko nga, is para siyang altar. So, doon ginagawa yung mga ceremony. So, as you can see, there is a geometrical shape doon sa letter A and sa letter B. There are triangles, perpendicular, the squares, the rectangles. So, sa letter B na, makikita nyo yung, pagkakaroon ng pagkakaiba ng mga triangles. Meron ng isosceles, may obtuse, and meron na ring acute ang triangles. So, hindi pa rin mawawala yung rectangles and squares during that time. So, sobrang galing ng mga Indian kasi during that time, nagagamit na talaga yung math as engineering and architecture sa paggamit para makapagtayo ng mga platforms of building or buildings. So, here, Sulba Sutras or the Sulva Sutras during the 8th centuries, long before Pythagoras listed several Pythagorean triples as well as a statement of simplified Pythagorean theorem for sides of squares and rectangles. So, yung Pythagorean theorem during that time, excuse me, ay ginagamit na sa mga squares and rectangles. So, sinasabi dito na bago pa daw malaman ni Pythagoras yung Pythagorean theorem is nagagamit na siya ng mga Indian. And it is stated or contained in Sulba Sutras. Nilalaman din siya ng Sulba Sutras. So, for you guys to know kung ano bang itsura ng Sulba Sutras, so ganito rin. Ganito yun. It is parang similar to the Sanskrit. Yan. Pero as you can see guys, there are geometrical shape as well. The triangles, the squares or diamond. I'm sorry, squares or diamonds. So yeah. So sabi dito, it seems quietly that Pythagoras learned his basic geometry from Sulba Sutras. So as you can see guys, so yung kanina, Sulba Sutras, these are the mathematics of Vedic period. So dito sa left picture or left photo, makikita niyo yung mga geometrical shape ng patterns ng squares and triangles. So while on the right side, parang katulad talaga ng pattern ng Sulba Sutras dito sa Pythagorean theorem ni Pythagoras. So, sinasabi na bago pa daw nalaman ni Pythagoras yung Pythagorean theorem or matuto siya ng kanyang basic geometry ay natutunan niya ito sa Sulba Sutras na nanggaling sa India. So now, the Sulba Sutras or Sulba Sutras is contained also geometric solution of linear and quadratic equations and give a remarkably accurate figure of square root of 2 obtained by adding 1 plus 1/3 plus 1 over 3 times 4 minus 1 over 3 times 4 times 34, which yields a value of 1.41425156 correct to 5 decimal places. So, as you can see, nagagamit nandito yung mga linear and quadratic equations na na-encounter natin today. And napatunayan dito na meron daw square root of 2. So, if you will have, kung confused kayo or naku-curious kayo kung ano ba talaga yung square root of 2, so you can, pwede nyo siya i-try i-add. I-try nyo to, lahat ng to. And baka makuha nyo to. So, try nyo lang. Wala namang masama. Confuse kaya. So, next. So, as early as the 3rd or 2nd century BCE, Jain mathematicians recognized 5 different types of infinities. So, those are the infinity in one direction, infinity in two direction, in area, infinite everywhere, and perpetually infinite. Ancient Buddhist literature also demonstrate a persistent awareness of indeterminate and infinite numbers, with numbers deemed to be of 3 types: countable, uncountable, and infinite. So, by the way, those Jain mathematicians are people. So, Jain are parang race dun sa parang area ng mga Jains ang tawag sa kanila. Kaya sila ang tinawag na Jain mathematician. So, naka-recognize nila yung different types of infinity. So, yun. So, it could be countable, uncountable, or infinite. So, pag countable, nabibilang pa yung infinite. Nabibilang pa yung numbers. Kapag uncountable, parang ito yung mga irrational numbers. And infinite, yung walang katapusan. So, move on. So, the earliest record usage of a circle characterized as a number 0. The earliest recorded usage of circle character for the number 0 is usually attributed to a 9th century engraving a temple in Gwalior in central India. So, yung first recorded of 0 ay naitala during 9th century sa Gwalior in central India. And before tayo mag-move on sa next slide, so dapat may tanong ako sa inyo na why 0 is important. Kaya lang hindi naman na na ano yung na-discuss nung parang live or naka-virtual. So, inalis ko na lamang dito sa slides. So, if you can really answer it, why zero is important, you can message me naman. Okay? So now, the earliest recorded usage of circle characterized as a number zero. So, yung circle ay kinakarakterize as a number zero. So, circle pa lang siya. Hindi pa siya oblong. Excuse me. Wala akong COVID. So, the earliest recorded usage of a circle character for the number zero is usually attributed to a 9th century engraving. So, it was credited to the 7th century Indian mathematicians Brahmagupta, or possibly another Indian Bhaskara the first. So, si Brahmagupta or si Bhaskara. So, mamaya magigets nyo kung bakit kinoconsider din si Bhaskara. Pero, it was first credit to Brahmagupta, yung zero. So, excuse me. So, this is the picture that the ancient Hindu symbol of circle with a dot in the middle. So, para siyang, ano doon? Yung dart, yun, yung may bullseye. So, ang tawag dito ay bindu or bindhu, symbolizing the void and the negation of self. So, parang binovoid or binabaliwala yung parang walang bilang. Ganon yung representation niya. So, it was probably instrumental in the use of a circle as a representation of concept of zero. Next, so let's move on to the Indian mathematicians. So first we have Brahmagupta. So si Brahmagupta was an Indian mathematician and astronomer who wrote two important works on mathematics, the Brahmasputa Siddhanta and the Kandakadhyaka. And he was the first mathematician to use the concept of zero. So, siya nga yung unang gumamit ng zero, but right now, people don't know where Brahmagupta's mathematics are derived from. So, si Brahmagupta ay meron dalawang important works on mathematics. So, yun, una ay Brahmasputa Siddhanta and the Kandakadhyaka. So, I don't know how to pronounce it. So, yan. So, I will be discussing the Brahmasputa Siddhanta and the Kandakhyaka. So, let's move on. So, Brahmagupta established the basic mathematical rules for dealing with zero. So yun daw. Kasi nga, yung zero is as a void or negation or baliwala or wala lang. So, 1 plus 0 equals 1, as well as 1 minus 0 equals 1, and 1 times 0 equals 0. So, Brahmagupta gave the first rules for dealing with zero as a number. So, sinasabi niya na when zero is added to a number or subtracted from a number, the number remains unchanged. So, hindi na yung nagbabago kung ano yung number na i-add or i-subtract natin sa zero. While a number multiplied by 0 becomes 0. Kung ano man yung number na i-multiply natin kay 0 ay magiging 0. So, yung concept na yan or yung principles ng zero na yan ay naggaling kay Brahmagupta. So, in dealing with positive fortune and negative debts number, so a debt or the negative number minus 0 is negative. A positive minus 0 is positive. 0 minus 0 is 0. So, kapag daw ang debt or ang negative, sinubtract natin kay 0, ito ay magiging positive. So, kapag ang fortune, sinubtract natin kay 0 or ang positive, sinubtract natin kay 0, ito ay debt. The product of 0 multiplied by a debt or fortune is 0. The product of 0 multiplied by 0 is 0. Kasi nga, any number multiplied by 0 becomes 0. The product or quotient of two fortunes is one fortune. The product or quotient of two debts is one fortune. One fortune. So, ang product or quotient ng dalawang negative ay positive. So, ang product ng o quotient ng dev at fortune or negative at positive ay negative. At ang product or quotient ng positive and negative is negative. So, yung rules na yan ay nanggaling kay Brahmagupta, which is really, really useful at is as in gamit na gamit hanggang ngayon. So, I remember when I was in high school, ang turo lamang sa amin ay si Mr. Lacorte. Nung ako'y high school, ang turo niya sa amin is, if you hate to love, you will hate. If you love to love, you will love. And if you hate to hate, you will hate. So, yun yung tinuro niya sa amin, which is relatively same as Brahmagupta's rules dealing with zero. So, next. So, Brahmagupta's theorem on cyclic quadrilateral. So, he established square root of 10, which is 3.162277 as a good practical approximation for pi, which is 13.141593, and gave a formula now known as Brahmagupta's formula for the area of a cyclic quadrilateral. So, yung sa formula ng area of a cyclic quadrilateral is nanggaling din kay excuse me, Brahmagupta. So, and as you can see guys, yung pi is also nanggaling rin sa kanya. Kaya lang mamaya I will show you yung pinagkaiba ng kay may Brahmagupta and do sa isa pang mathematician. Magkakaroon sila ng pagkakaiba dun sa square root. So as you can see here, the line BD is perpendicular to AC. Line AC. Line BD is perpendicular to line AC, which is true. It forms 90 degrees of angle. While line EF is perpendicular to line BC, which is true. Here. So, it equals to line AF is equal to line FD. So, yan. So, sa kanya to. So, it is ginagamit sa cyclic quadrilateral area. So, next. So, now, let's go to the work of Brahmaguptas. So, first, we will discuss the Brahmasputa Siddhanta. So, Brahmasputa Siddhanta is one of the first books to provide concrete ideas on positive numbers, negative numbers, and zero. So, yung ginamit ko kanina na yung dev and fortune or yung the product or quotient of dev and fortune is dev. So, nilalaman din siya nitong Brahmas Puta Siddhanta. So, sinasabi din dito, according to my research na ang negative numbers was first used by the Indians, which is si Brahmagupta nga. And Brahmasputa Siddhanta is yung work niyang Brahmasputa Siddhanta ay naglalaman ng positive numbers, negative numbers, and zero of concrete ideas. So, I'm sorry hindi ko na pala na-download yung itsura ng books ng Brahmasputa Siddhanta kasi wala akong makitang reliable image ng Brahmasputa Siddhanta. So, next is the Kadyaka. So, Kadyaka is an astronomical treatise written by Indian mathematician and astronomer Brahmagupta in 665 after death. The treatise contains 8 chapters covering such topics as the longitudes of the planets, diurnal rotation, lunar and solar eclipse, rising and settings, the moon's crescent, and the conjunctions of planets. So the Kadyaka is about the astronomy and as well as mathematics. And parang according to my research as well, parang itinuturing siya sa kauna-unahan ding research tungkol sa astronomy. Yeah. So, marami tong chapters. It has 8 chapters. So, nandito naman yung mga, kung ano yung cover ng 8 chapters na yan. So, let's move on. I'm sorry, hindi ko rin pala na-download yung itsura ng books na yon kasi wala din talaga ako makitang reliable source or reliable na source ng books na yan. So now, I have a question here. If you run out of letters from the alphabet, how would you name or represent an unknown variables? So usually we use from A to Z. So nabasa ko lang to sa isang, basta nabasa ko to sa isang math kineming question. So if I were to represent an unknown variable, siguro I would choose those, kung kayo ay siguro, marami 'di ba? Ang hirap, pwedeng names. Pero kung ako siguro, yung mga symbols sa periodic table of element. Kasi sobrang dami nun. So, hindi lang siya 26 or 28 katulad ng alphabet. So, yun lang. Share ko lang. So, next. So, ito nga, connected dun sa tanong na yon. Brahmagupta also used the initials of the names of colors to represent unknowns in his equations, one of the earliest intimations of what we know as algebra. So, ang ginamit niya is a color. Like red is R, W is Y is for yellow, W is for white. So, ganun yung ginawa niya. And now, na ginagamit natin is algebra. Na meron tayong subject din kay ma'am na college in advanced algebra. Diyos ko, pinahihirapan. So, now, let's move on. So, the golden age Indian mathematicians. So, nung Golden Age, Indian mathematicians made fundamental advances in the theory of trigonometry and the method of linking geometry and numbers first developed by the Greeks. So, as I said earlier, yung iba nilang, meron dong mga parts na sinasabi na nauna daw na develop ng Greeks. So, inadapt nila yon and they made another fundamental advances sa trigonometry, sa geometry, na related sa mga dinevelop na before ng Greek. So, parang in-innovate lang nila or mas parang in-evolve nila in a higher level. Parang ganon. So, no. Next. So, they use ideas like the sine, cosine, and tangent functions. So, according to my research, ang sine, cosine, and tangent functions was first used by the Indian mathematicians. And it is one of their biggest contribution when it comes in mathematics. Kasi sobrang gamit na gamit yan, lalo na sa geometry. Yan, favorite ko. So, yan. Sa mga vectors, nagagamit yan. So, next. So, as I said din earlier, or a while ago, na yung Pythagorean theorem was firstly learned basic ni Pythagoras ay sa mga Indian. So, next. So, here, an example of Indian trigonometry tables which shows that an angle of 1/7 degrees indicates triangle sides with a ratio of 400:1. Meaning na yung araw daw ay 400 times na mas malayo sa Earth kumpara sa Moon. Ibig sabihin nito, nire-represent nila na parang pinapatunayan dito na mas malapit yung Moon sa Earth kumpara sa Sun. So, yun. So, that's the, part of their astronomical studies. So, next. Oh my God. Now, the Surya Siddhanta. So, the Surya Siddhanta is also a book, the oldest book on astronomy known to a man. So, as you can see, as you can read, the oldest book on astronomy known to a man. So, ang gumawa niya is Indian mathematicians din. So, yan. So, next. So, the Surya Siddhanta. So, this text is known from 15th century CE palm leaf manuscript. So, natagpuan siya ginamit siya ng 15th century and ginagamit siya ng mga palm leaf. Kaya yung mga familiar ka sa palm leaves, yung parang um, sa niyog, parang mga ganon, or mga buli, parang ganon, yung ginagamit nila na panulat or writing materials or writing ways para makapagtala ng mga contents do sa pinag-aaralan nila. Of course, including tungkol to sa math or astronomy. So, the Surya Siddhanta also describes rules to calculate the motion of various planets and the moon relative to various constellations and calculates the orbits of various astronomical bodies. So, the Surya Siddhanta, sobrang napakalaking natutulong nito kasi biruin nyo, from other, nung ako'y high school, ang nalalaman ko lang is mga parang foreign, bukod sa Indian, like mga Westernians, sila yung nag-aaral tungkol sa mga planets, sa mga constellations, yan, ang alam ko lang sila. Pero with this, nalaman ko na Indian pala yung nauna mag-aral ng tungkol doon. So, wow, na-amaze lang talaga ako ng sobra. So, yan. So, ultimo yung various planets na yung moon relative to various constellations, pinag-aralan din doon. So, yan. As well as the calculates the orbits of various astronomical bodies. So, it includes the asteroids, etc., etc. So, now, let's move on to another mathematician, si Aryabhata or Aryabhata. So, Indian mathematician and astronomer. So, he produced categorical definitions of sine, cosine, versine, and inverse sine, and specified complete sine and inverse sine in 3.75 degrees, interval from 0 degrees to 90 degrees to an accuracy of 4 decimal places. So, siya yung nag-produce ng mga categorical definition ng sign, kung ano ba ibig sabihin ng sign. Kung first use, ginagamit si Brahmagupta, ginagamit yung ginawa niya yung sign, or yung mga Indian ginawa nila yung sign and cosine and tangent. So dito naman kay Aryabhata, nabigyan na siya ng definitions kung ano-ano yung pagkakaiba nila. So yan. So, he also demonstrated solutions to simultaneously quadratic equations and produced an approximation for the value of pi equivalent to 3.1416, correct to 4 decimal places. So here, as we watch kanina, kung napanood nyo kanina or nabasa nyo kanina, si Brahmagupta is nag-produce din siya ng tungkol sa pi, which is equivalent to as well as 3.1415. Then, now, si Aryabhata naman is also nag-produce din ng another approximation for the value of phi, which is equivalent to 3.1416. So, infinity as the reciprocal of 0. So, as I can see kanina, so it's either Brahmagupta, diba, or si Bhaskara yung nakaunang gumamit ng 0. So now, dito sinasabi kung bakit si Bhaskara ay kinoconsider din na unang gumamit ng 0. So, Bhaskara the second, 12th century. He is credited with explaining the previously misunderstood operation of division by 0. He noticed that dividing 1 into 2 pieces yield as a half. So, 1 divide 1 half equals 2. Similarly, 1 divide 1/3 equals 3. So, parang na-curious lang siya na do sa paggamit ng 0 sa division. So, now, pinapaliwanag niya dito na papaliwanag niya dito na yung 0 is equivalent to infinity and can be the reciprocal infinity can be the reciprocal of 0. So, ito yung tanong doon sa question ni ma'am na isa, yung 1 to 5, which is hindi ko nasagutan kasi nagloloko yung LMS ko. Sorry. So, yun. So, Bhaskara. So, now. So, 1 divided 1 half equals 2, which is true. 1 divided 1 third equals 3, which is true. As well as y divided 1 fourth equals 4. 1 divided 1 fifth equals 5. And so on and so forth. So, now, dividing 1 by smaller and smaller fraction yields a larger and larger number of pieces. So, kapag daw dinivide yung 1 sa mas maliit as mas maliit pang fractions, lumalaki ng lumalaki yung number. So, ganun din, kapag dinivide ang 1 sa pieces of zero size would yield infinitely many pieces. Mas maraming pieces yung mangyayari. Di-divide mo sa maraming pieces, di ba? So, kasi kinukonsider ang zero as the least number. So, mas maraming pieces yon. So, it indicates that 1 divided 0 is equal to infinity. So, meron dito explanation. So, as you can see in the screen, as x gets bigger and bigger, like 1 over x approaches 0. Diba? So, kaya nga yung x hindi pwedeng maging 0. Kasi, kapag yung x naging 0, magiging infinity or undefined. Kasi, yung x is the denominator. Now, conversely or kabaligtaran, as x gets smaller and smaller and approaches 0, 1 over x approaches infinity. So, kapag ang x ay mas lumiit ng lumaliit at papalapit ng papalapit kay 0, yung 1 over x ay nag-a-approach sa infinity. Kaya, kinukonsider ni Bhaskara na 0 is the reciprocal, infinity is the reciprocal of 0. So, yes, meron daw pong, as dito sa report ko, merong reciprocal ang 0. Okay? So now, however, Bhaskara also made important contribution to many different areas of mathematics from solution of quadratic, cubic, and quartic equation. So, hindi lang si Yabarata or Brahmagupta yung may quadratic and contribution sa mga quadratic equations or cubic equations. Pati si Bhaskara, meron din po. So now, the Kerala School of Astronomy and Mathematics. So, it is a school. It was founded in the late 14th century by Madhava of Sangamagrama. So, Sangamagrama is a place sa India and Madhava is a mathematician. So, biruin nyo, during that time, meron ng School of Astronomy and Mathematics in India. So, relate nyo to. Parang imagine, kung ang Philippines ang merong ganyan during that time, siguro hindi natin hini-hate yung math. That's why Indian loves math. Kasi nga, sa letra ng G, 5, 6, utang ka ba? India. Ganon. So, yun. Nakakatuwang isipin na during that time, wow, I was really amazed na meron na silang school na tumatalakay sa astronomy and mathematics. So, as well as, it developed infinite series approximations for a range of trigonometric functions including sine, sine, cosine. So, dito rin nagsimula yung mga infinite series ng pag-approximate ng range sa mga functions katulad ng pi, sine, and cosine. Pero, yan. Mamaya pala yung pero. So, si Madhava. So, ito pala si Madhava of Sangamagrama. So, from 1340 to 1425. So, ilang taon siya? 60 plus 25, 85 years old siya nung namatay. So, pi is infinite series. So, kanina, di ba, si Brahmagupta is pi is equals to square root of 10. Ngayon, si Madhava is pi is equal to square root of 12 plus 1 minus over 3 times 3 plus 1 over 5 times 3 squared minus 7 times 3 squared dot. Well, I guess 21 terms, 11 digits. So, 21 terms, 11 digits hanggang doon yung ellipsis nun. So, as you can see guys, 3, 5, 7. So, puro odd numbers siya. So, if you are really confused or curious about doon, pwede nyo itry. Basta ang ilalagay nyo lamang ay puro odd numbers. So, 3 times 3 plus 5 times 3 squared minus 7 times 3 squared. Well, parang alternate lang ata yung tawag dito, operations nila. Parang minus, plus, minus, plus, minus, plus. So, kung talaga na-curious kayo, pwede nyo siya itry. So, the golden age of Indian mathematics. So, ito na yung pera ko. During 5th to 12th century, nagkaroon ng issue. So, ang issue dito is some claims of plagiarism by later European mathematicians. It seems that Indian contribution to mathematics have not been given due acknowledgement until very recently in modern history. Hindi hindi ina-acknowledge or hindi tinatanggap ng marami or ng karamihan kasi sinasabi daw na parang ginaya lang or parang tinulad lang yung mga gawa nga ng mga European or ng mga Western yan na nababanggit ko kanina. Which is, pero until very recently, yan, na-acknowledge naman na siya. Kaya, yun. So, ganyan lang. So, nakakalungkot lang na ikaw yung original, pero hindi pala. Parang ganon. Yung nangyari dito ang issue. So, now, let's move on to Chinese mathematics. So, even as the mathematical development in the ancient Greek world were beginning to falter during the final centuries BCE, the burgeoning trade empire of China was leading Chinese mathematics to ever greater heights. Excuse me. Nagkakape kasi ako. So, yan. So, of course, meron na nung silang ina-adapt na mga mathematical concept and nanggagaling to sa mga Greeks. Pero at that time pa rin, meron pa rin silang during nung Empire ng China, meron pa rin silang sariling way ng mathematics. So, those are these. So, examples, the ancient Chinese number system. As you can see, 1 represent one number, 2 represent 2, 3, 4 stick, 5 stick. Yan. So, ganyan po yung number nung una. Nung ancient Chinese number. Pero, meron akong research na hindi ko na lang siya in-include kasi maggugulo-gulo. As the time goes by din, nababago din yung representation na number. Kung dyan is 1 equals 1 stick, meron naman sa iba na parang Mandarin na yung sulat. Pero hindi ko na kasi talaga siya mabasa. So, yan. Share ko lang. So, the Chinese number system. The Chinese numeration system has a characters that correspond to the numbers 0 to 9. 0 to 9. Unlike the number system where used to use Chinese also special characters to represent 10, 100, 1,000, 8,000, as well as other multiples of 10. So, as well as gaya ng Indian, meron na rin silang paggamit ng hundreds, tens, thousand. Parang siyang Roman numerals na 1, VX, L, M, C, D. So, parang ganun yung sinasabi dito. Next. So, use small bamboo rods arranged to represent the numbers 1 to 9, which were then placed in columns representing units, tens, hundred, thousands. So, now, here are the pictures again. So, one bamboo, diba? One bamboo rod is equals to from 1 to 9. So, here, from 1 to 5, nagagawa pa siya, pwede pa siyang isa-isa. Pero pagdating sa 6, yung 5 ay magiging isang number na horizontally or pahalang. Tapos pag dinagyan mo lang siya ng isang number na pataas or patayo, magkakaroon na siya ng 6 as well as ganun. Sa 7, ganun din sa 8 and 9. So, ganun yung sistema ng pag-number dun sa China. So, next. So, ito na nga. Nagkaroon na ng pagbabago dun sa number. Yung 0, hindi ko mabasa. Yung 1, possible kasi parang bamboo lang. 1, 2, 3. Pero pagdating sa 4 hanggang 10,000, hindi ko na mabasa. Hindi ko na masyado ma-represent. So, ganun yung sistema ng Chinese nun. So now, familiar with this? Of course, the abacus. The use of abacus, also called counting frame. Ang tawag din dito ay sauna. Swana. Yan. Is often thought of as a Chinese idea, but its origin is still unknown. So, sinasabi na hindi parang sinasabi na ito ay nagmula sa China, pero yung pinagmula nito ay hindi pa rin alam. Kasi there are different parts like Greece or sa mga European countries, ginagamit na rin ang abacus. So, ito ang ginagamit siya sa pag-multiply, pag-add, pag-subtract, pag-divide, square root, and cube root. Pero kung paano gamitin yon, hindi ko alam. Kasi hindi pa ako nakakita ng abacus sa totoong buhay. So, next, the Lucian magic square. Squares of numbers where each row, column, and diagonal added up to the same total were regarded as having great spiritual and religious significance. So, itong Lucian magic square ay nire-represent parang patungkol sa relihiyon. So, nakatala dito na yung 492, this is the 492. Yan. Nagre-represent naman dun sa, yung parang mga dots, makikita nyo, yung dots, nagre-represent kung ilang number meron para sa ano. So, it's 3 by 3 column or 3 by 3 box. So, kapag inad nyo siya ng vertically, horizontally, or diagonally, ang magiging sagot nyo is 15. So, ito ay para bang, madalas nating nakikita ay sa mga logics. Madalas nating nakikita ay sa mga logics. So, parang ganun. Kaya, sobrang galing ng mga Chinese sa logic. Lalo na pagkwentahan ng pera. Next. So, Jiwang Zhuanshu. So, this is the Jiu Shang Zhuanshu. This is the books na naglalaman noong kay Lu Shu na yon. So, now, next. Examples of Chinese method of solving equation. So, if 1 plum and 3, so ito naman yung example ng solving equation. So, yan. The Chinese method of solving equations. So, if 1 plum and 3 peaches weigh a total of 750 grams and 2 plums and 1 peach weigh a total of 500 grams, how much does a single peach and plum weigh? So, first, double the content of the first scale. So, parang yung first given na 1 plum and 3 peaches, dodoblehin mo lang. So, pag-a-add natin siya. So, now, nung na-add na siya, 750 plus 750 is 1,500. Subtract. Now, kung ano yung subtract, isusubtract natin doon sa second set of scale or doon sa second given, which is 500 grams. So, cancel nyo yung dalawang plum at isang peaches. Ang matitira na lamang ay 5 peaches, which is equivalent to 1,000 gram. Therefore, ang single peach ay nagwe-weigh ng 200 gram. Kasi, divide mo yung 1,000 grams sa 5, mag-i-equal siya ng 200 gram. Samantala, take the peach of the second scale. So, i-minus nyo naman yung second scale or yung second given na 500 sa 200, which is 300 grams. So, dalawa yan, divide nyo sa 2, magiging 150. So, basically, ito rin yung madalas natin nakikita sa Facebook na mga logics. So, nagmula pala siya sa Chinese hanggang ngayon, which is ginagawa na nating recreation. Diba? So, that's the contribution of Chinese na buhay pa rin hanggang ngayon. Now, last, or I guess this is the last, the Chinese remainder theorem. Chinese also started to pursue more abstract mathematical problems, although usually couched in rather artificial practical terms, including what has become known as the Chinese remainder theorem. So, marami na rin silang, nagpo-pursue sila ng iba't ibang abstract mathematical problems, pero, ayun nga, artificial practical terms lang yung nangyayari. And so, one of the practical terms na ginagamit natin hanggang ngayon is the Chinese remainder theorem. So, this is the example of the Chinese remainder theorem. If a collection of balls are arranged in rows of 3, there is one ball left over. So, there's one ball left over. 3. So, assume that, sinasabi dito that the Chinese remainder theorem proves that the smallest number of balls must be 52. So, if this is 52, and these are, arranged in rows, so lahat ng ito is 51. If, by rows, by trees, may matitirang isa. So, if arranged in rows of 5, there are 2 balls left over. Kasi 5 times 10 is 50. May matitirang dalawa. If arranged in rows of 7, there are 3 balls left over. Kasi 7 times 7 is 49. May matitira pang isa. Ay, 3. So, ganyan yung reminder theorem ng Chinese, which is ginagamit natin until now sa pag-remainder kung ano yung natira. Lalo na sa mga product. Usually, madalas ito tinuturo ay sa mga elementary, yung pag-remainder, di ba? Doon naman siya unang tinuturo. So, sa Chinese pala nang galing yung idea ng remainder theorem. So, yun.